Inhomogeneous medium is a medium in which the refractive index changes from position to position. Okay, so you can use the Huyghens principle to evaluate the distortion of the wavefront. Okay, now we make a very simple example, but that you might find in the test. Example. Very simple example. So think, for example, you have a plane wave. And think that at a certain time, this plane wave accesses a region in which here on the bottom part, the refractive index is N2, and on the top part, the refractive index is N1. So you have two different refractive indices. Okay? And now, and say, for example, that N1 is smaller than N2. We make this assumption. We could make the reverse. Now we ask ourselves, what is the shape of the wavefront at the exit of this system? So you have this plane wave that is entering here until when it moves in vacuum, it will remain a plane wave, a flat wave. Then it accesses this region. Okay. Now, what does it happen here? Here, you have a propagation speed V2 that is C over N2. Here you have a propagation speed V1 that is C divided N1. Since N1 is smaller than N2, the speed V1 is larger than V2. So the two speeds are different. Okay? So when propagating inside the medium, the wavefront on the top part will run faster, and the wavefront on the bottom part will run slower. So you will have something like this after some time. Then you will have something like this after some time. So when the wavefront is here, it is like this. And then when you get here, the two wavefronts will be like that. Okay? So there is a change of the shape of the wavefront due to the retardation that you have in a medium with a refractive index N2. You are delayed. Okay? And at the exit, then you have this and that. Okay? How is it if, say, this is the distance, the thickness of your materials? Okay? And let's assume that if this is the x-axis, this is the position 0. Okay? What is the phase that accumulates the first field, and what is the phase that accumulates the second field? So in the region number 1, okay, how is it described, your plane wave? It is a plane wave that has got a certain amplitude. Let's say it is E0, okay? Sinus, the wave number in this medium, that is K1, okay? And if you have propagated by a distance d, how much you covered a distance d, okay? Minus omega t, you have a forward propagating wave. In the medium 2, you have that the field is given by such an expression. Let's take into account that the two amplitudes are the same, okay? And you have sinus k2d minus omega d. So you see that the two phases are different. This is the phase of the wave 1. This is the phase of the wave 2. What is the phase difference between these two wavefronts? It is, let's say, phi 1 minus phi 2. So this is k1 minus k2 times the thickness of the material. You accumulate a phase delay that is given by that. And this can be written, if you remember the definition of K. What is the definition of K? Is written as omega divided by the propagation speed. Remember this? You remember when we wrote the dispersion of light, that is a line, omega is equal to k times the speed of propagation. Okay? So you can write omega divided V1 minus omega divided V2 times d. Omega can be factorized. So this is omega d. 1 over V1 is N1 divided by C minus N2 divided by C. Okay? So we can, let me write on another board. So we have omega d N1 minus N2, what was it? Divided by C. This is delta phi. And so remember that this is K naught, okay, times D times the refractive index difference. So if there is a difference of the refractive index, you accumulate a phase that is the refractive index difference, delta n, times the thickness of your material. Of course, the more is thick the material, the more phase you accumulate, times K naught. And remember that K naught is 2 pi over lambda naught d N1 minus N2. Okay? Okay?
Okay.
This is the phase difference. Now, what does it happen if this phase difference is 2 pi? What does it happen? You have a plane wave, okay? These are wave fronts. And remember, when you sketch this, you think this is the wavelength. These are wave fronts. When you get inside these two media, the wavefronts are delayed in to a different extent. If delta phi is equal to pi, what does it happen? It happens that these wavefronts come out, okay? And this wavefront here is delayed here. This wavefront here is delayed here. But if the delay is 2 pi, this you reconstitute a plane wave again. So if the phase shift is 2 pi, you reconstitute a plane wave. Okay? And look, what is the condition here to have delta phi equal to 2 pi? You have 2 pi over lambda naught times d times n1 minus n2 must be equal to 2 pi. 2 pi and 2 pi go away, and you get that this difference here multiplied by lambda naught must be equal to the wavelength. This justifies the reason why in optics you introduce a quantity that is named optical path. Okay, so in optics you introduce a physical quantity that is named optical path. The optical path that you can write like this is defined as the refractive index of the medium in which you are propagating times the geometrical distance that you are making in the medium. So if you go from here to here, from A to B, and the length, the geometrical distance is L, okay, you have an optical path, and we named L, an optical path that is equal the refractive index times the geometrical path. And the larger it is the refractive index, the greater it is this optical path. So the same geometrical distance corresponds to a different optical path. Now look at this expression here. D times N1 is the optical path you have in the medium 1, minus the optical path that you have in the medium 2 must be equal to the wavelength lambda naught. So the difference between the two optical paths must be a multiple of the wavelength. Then you get this case here. Okay? So to get a phase shift that is 2 pi, you must have the difference of the optical paths is a wavelength exactly. If you want a phase shift of pi over, of pi, the difference of the optical path must be half the wavelength, and so on. And this is just to introduce the optical path. Now, are there questions? This? No. The last brick that we add to our, let's say, summary of general physics is some concept about polarization of light. Of electromagnetic waves. Okay. Now, when we discussed the plane wave, we said, okay, let's make a very simple model. We assume that the wave is plane. Then we said, okay, if we work hard on the Maxwell equations, we find out that the electric field must be in the plane. So the electric field has components that must be along X, sorry, I used the wrong letters. X, Y, A, Y, A, Z, okay? These are the components. So there is no component of the electric field along the propagation direction. That this is the propagation direction. Then we said, okay, let's make a very simple model and let us assume that the field is polarized along the y direction. So we turned the electric field and we studied only the case where the field is along y. And the wave equation becomes a scalar equation, very simple to solve. Okay? But in general, the electric field can have both a y component and a z component, and both of them can be different from 0. So in general, this electric field will have both a y and a z components. Sorry, there are no equals. And the z components. Now, if for the sake of simplicity, we think of an harmonic wave, in the case of a harmonic, and we remind that this is also called the monochromatic wave, so there is one single frequency component, then these two fields can be written as an amplitude times sinus kx minus omega t, if we think of a forward progressive wave. So there is the minus sign. And let me, say that here there can be a phase phi1. And the field along z can have an amplitude Az sinus. It will have the same wave number, the same angular frequency, and possibly another phase, P2, phi2. Okay? So in general, we can decompose the electric field in two components, one along y and one along z. Okay? Now, this is the general expression of the field associated to an electromagnetic wave, a plane wave and harmonic wave. Now, there are several cases that we can study. And what are these cases? Let me write it down. Now, what are the cases we can have? One, Az is equal to 0. So the Z component is missing. Okay? So the field has got only Y component. This is named linear polarization along Y. So we say that the electric field is linearly polarized along the Y direction. Very often, when you have a laser, light coming out from a laser is vertically polarized. So the light, the field oscillates in the vertical plane. Okay? Then you can have, of course, AY equal to 0. Then you have linear polarization along Z. The field is horizontally polarized. Okay? Then you have a third case. And the third case is AZ different from AY different from 0. Both amplitudes are different from 0, and the two phases are the same. Now, I will write it here. What does an observer see when he observes the wave that is coming towards him? Say you are an observer here. This is your eye, okay? And light is coming towards you, okay? You see the y-axis, you see the z-axis, the x-axis is towards you, okay? And you see that along the y direction, the field can have a y component. Along the z direction, the field can have a z component. So this is x coming towards you. And this is, sorry, ay, this is minus ay, this is minus az, this is az, okay? So along the x direction, you see that the electric field goes back and forth, back and forth, back and forth like this. Along the y direction, you see the field that oscillates like that, but they do it in phase. What does it mean? When the z component is at a minimum, the y component is at a minimum. And so the composition of these two gives you a point that is here. So the field is here, okay? So you see the total field that is oscillating along this direction, back and forth, because the two components are changing in phase. So when you are here, you are here. When you are here, you get here, because the two sinusoids oscillate in phase. Okay? So you have the so-called linear polarization at an angle theta, where theta is this angle here. And of course, you can calculate this angle theta. The tangent of the angle theta must be the ratio of the two amplitudes, A1, AY divided by AZ. Okay? Now, what does it happen if the two amplitudes are the same and different from 0, and the two phases are the same? In this design here, you get that you have a square, and the angle here is 45 degrees. So you have the linear polarization at 45 degrees. Linear polarization at 45 degrees. So an observer watching the electromagnetic wave that is going towards him sees the field oscillating at 45 degrees, and it remains in that plane. The polarization keeps linear. Now, there is a fifth case. Let me change blackboard. There is a fifth case, A1, AY different from AZ, different from 0. So the two amplitudes are different from each other, okay? And the two phases are different by pi over 2, by 90 degrees, plus or minus by 90 degrees. Then one observer, he sees the same rectangle here, you have two fields oscillating between two different extrema, but the two oscillations are out of phase by pi over 2. So what you see is an elliptical shape, because when the Z field is at a maximum, since you have a pi over 2 shift, the Y field is at a 0. When the Y field is at a maximum, the Z field is at 0, and so on. And so you describe an ellipse in the plane. And this ellipse can have a rotation direction that is clockwise or counterclockwise, depending on the phase shift here. So phase shift plus pi over 2 is clockwise, minus plus over 2 is counterclockwise. Okay? This case is named elliptical, let's say, not elliptical, canonical, elliptical polarization. Why canonical? Because the axis of the ellipse coincide with the Z and Y axis. So it is horizontal, this ellipse. Now, the sixth case of polarization is when AY is equal to AZ, different from 0, and the two phases differ by pi over 2. Which case is this? Circular polarization, because the two fields oscillates between the same two extrema, and you have the so-called circular polarization. Circular polarization. Now, the most general case, C7, is the two amplitudes are different, the two phases are different, but without no, let's say, the difference between phi 1 and phi 2 is not pi over 2, can be any number. Then what you see with the same meaning of this rectangle that you see here, you see here that you get an ellipse that is rotated like that. So you have non-canonical elliptical polarization. Right or left-handed. So clockwise or counterclockwise. Now, therefore, we always have to keep in mind that in general, if you have an electromagnetic wave, it has two components of the electric field, and depending on the amplitude and on the phases of these two components, you can have many states of polarization. Linear along Y, linear along Z, linear along a given direction, linear at 45 degrees, elliptical, canonical, circular, and generally elliptical. These are the states of polarization of polarized light. Now I ask you, What is the polarization of sunlight? One of you here in the hall is saying non-canonical elliptical. And why is she saying that? Because this is the most, let's say, free case, no? Do you agree with that? Do you agree with that? Be careful. Sunlight is not polarized. These are the states of polarized light. Sunlight, when you take sunlight, and one observer looks at sunlight, at a certain moment, the field is here. 1 second later, it is here, then 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 it is here. And these jumps are completely random. And so you see that the field rotates without any given rule on the rotation of the field. So sunlight is not polarized. Therefore, it cannot be described by in any of the cases that we have given before. Okay? To polarize sunlight, you need to take a polarizer, say something that polarizes light, then you get linear polarization. Light from your light from the screen of your laptop, how is it, the polarization? It's linear polarization at 45 degrees, okay? Because you have liquid crystals inside. The 3D eyeglasses, the 3D, not the green and red that work with absorption. The 3D eyeglasses, they are circularly polarized on one eye and circularly polarized counterclockwise the other. Okay? Your cellular phone, how is it polarized? The light coming from your cellular phone, from your tablet. It was linear as the TV screens, okay? But then there was a problem. That if you are at the seaside and you, for example, you own a motor yacht, say 30 meters long, you are a very rich man, you own a motor yacht. Then switch it on and you start in the sea. Oh, this sea is really noisy because there is the scatter of light of the sun. What do? You wear eyeglasses, but you are very rich. And you have polarized eyeglasses. You paid more, no? These are polarizers, okay? And if that is linearly polarized, if you turn the tablet and it is linearly polarized, if the polarization that it emits is not transmitted by your eyeglasses, you will not see anything. So if you have an old cellular phone and you are in your car and you're using it as a navigator, if you turn it, it becomes black. You don't see it anymore with eyeglass. And then you need to rotate. But if you rotate and then by mistake you turn your head, then you will not see it. Therefore, there is a plastic sheet on top of that is randomizing the polarization to avoid this effect. To make that it is independent of rotation on detector and emitter. We shall deal with this a bit later when we will make how to polarize light. Okay? But if you have polarized eyeglasses, or a friend of yours has got them, put in front of the computer and rotate them. You will see the difference. Okay. And what time is it? 48. We have a break, a quarter of an hour break, and then we start again. I don't like to give 2.5 hours lectures. I really hate it, this. So I give you the rest, and then if there is any particular reason you want to shorten the lectures, we can make shorter breaks, but I want to keep this. So quarter of an hour, you relax.